Hello everyone. In this lecture we are gonna start and study the automotive systems. In the beginning the automobile looked like the horse and we'll move to the starting and charging systems. The starting system is responsible for getting the engine started when the ignition keys turn to the start position and we'll move to the starting and we'll move to the start. Hello everyone. In this lecture we are gonna start and study the automotive systems. In the beginning the automobile looked like the horse-drawn carriage it was designed to replace. So the automobile changed when the roads became paved and more people owned cars. Manufacturers tried to sell more cars, concerns for safety and environment to grow, and a new technology was developed. All of these changes resulted in automobiles that are more practical, more affordable, safer, more comfortable, more dependable, and faster. Although many improvements have been made to the original design, the basics of the automobile have changed very little. Nearly all today's cars still use gasoline engines to drive two or more wheels. Steering system is used to control the direction of the car. A brake system is used to slow down and stop the car. A suspension system is used to absorb road shocks and help the driver maintain control on a bumpy roads. And there are major systems are mounted on steel frames and the frame is covered with body panels. The body panels give the car its shape and to protect those inside from the weather and dirt. The body panels also offer some protection for the passengers if the automobile is in an accident. Let's move to the design evolution. Not too long ago, nearly every car and truck was built with body-over-frame construction, rear-wheel drive and symmetrical designs. Today, nearly all cars do not have a separate frame. Instead of the frame and body are built as a single unit called a unibody. Most pickup trucks and large SUVs still are built on a frame. Another major influence to design was the switch from the rear-wheel drive to front-wheel drive. Making this switch accomplished many things, the most notable being improved traction at the drive wheels, increased interior space, shorter hood lines, and a very compact drive line. Because of the weight and loads that pickup trucks are designed to move, most remain rear-wheel drive. Perhaps the most obvious design change through the years has been body styles. Body styles have changed to respond to the other design consideration and to trends of the day. So we have the body over frame construction. In body over frame construction, the frame is the vehicle's foundation. The body and all major parts of the vehicle are attached to the frame. The frame must be strong enough to keep the rest of the vehicle in alignment should a collision occur. The frame is an independent separate component that is not rigidly attached to the vehicle's body. The body is generally bolted to the frame. Large, specially designed rubber mounts are placed between the frame and body to reduce noise and variations from entering the passenger compartment. Quite often 2 layers of rubber are used in these pads to provide a smoother ride. The frame rails are made of stamped steel which are welded together. Some frames are made by a hydroforming process which uses high-pressure water rather than heat to shape the steel into the desired shape. Also, we have the utilized construction. A unibody is a stretched hull structure in which each of the body parts supplies structural support and strength to the entire vehicle. Unibody vehicles tend to be tightly constructed because the major parts are all welded together. This helps protect the occupant during a collision. However, it causes damage patterns that differ from those of body-over-frame vehicles. Rather than localized damage, The stiffer sections used in a unibody design tend to transmit and distribute impact energy throughout more of the vehicle. Let's move to the body shapes. Various methods of classifying vehicles exist. Vehicles may be classified by engine type, body frame construction, fuel consumption structure, type of drive, or the classification most common to consumers, which are body shape, seat arrangement, and number of doors. 8 basic body shapes are used today. The first one is the sedan, a vehicle with a front and back seats that accommodates 4 to 6 persons, is classified as either a 2 or 4 door sedan. Often a 2-door sedan is called a coupe. The next shape is the convertibles. Convertibles have a tiny roofs that can be raised or lowered. A few late model convertibles feature a folding middle roof that tucks away in the trunk when it's down. Some convertibles have both front and rear seats. Those without rear seats are commonly referred to as sport cars. Another shape we have is the liftback or hatchback. The distinguishing feature of this vehicle is its rear luggage compartment. Access to the luggage compartment is gained through an upward opening hatch type door. This design curve can be 3 or 5 door model. The third or fifth door is the rear hatch. Also, another design that we have is the station wagon. A station wagon is characterized by its roof, which extends straight back, allowing spacious interior luggage compartment in the rear. So the rear door, which can be opened in various ways depending on the model, provides access to the luggage compartment. Station wagon typically have 4 doors and can have space for up to 9 passengers. Also, another shape that we have is the pickups. Pickup truck body designs have an open cargo area behind the driver's compartment. There are many varieties available today. There are compact, medium-sized, full-sized, and heavy-duty pickups. They also can be had in 2, 3, or 4-door models. Some have extended cab areas with seat in the back of the front seat. They are available in 2-wheel drive, 4-wheel drive, or all-wheel drive. Also, we have the vans. The van body design has a tall roof and totally enclosed large cargo or passenger area. Vans can seat from 2 to 12 passengers, depending on size and design. Basically, there are 2 sizes of vans, mini and full size. The most common are minivans. Another shape that we have is the sport utility vehicles or SUVs. SUVs are best described as multi-purpose vehicles that can carry a wide range of passengers. Depending on their size and design, a good majority of SUVs have a 4-wheel drive, although some do not. Most small SUVs are based on automobile platform and take on many different looks and features. Mid-size SUVs are larger and typically offer more features and comfort. There are many large SUVs available. These vehicles can seat up to 9 adults and tow up to 6 tons. Also, we have the crossover vehicles. These automobiles look like an SUV but are built lighter and offer fuel efficiency. They are actually a combination of station wagon and an SUV. They have SUV features but are not quite the same size. The basic construction of a crossover vehicle leads to a less truck-like ride than normal SUV. They also are not designed to tow a heavy loads or for off-the-road use. And we'll move to the starting and charging systems. The starting system Hi, and we'll move right now to the basic engine. The engine pro. Hello everyone. In this lecture, we are. Hello everyone. In this lecture. Hi, and we'll move right now to the basic engine. The engine provides the power to drive the wheels of the vehicle. All automobile engines, both gasoline and diesel, are classified as internal combustion engines because the combustion or burning that creates energy takes place inside the engine. Combustion is the burning of an air and fuel mixture. As a result of a combustion, a large amounts of pressure are generated in the engine. This pressure or energy is used to power the car. The engine must be built strong enough to hold the pressure and temperatures formed by combustion. Diesel engines have been around a long time and are mostly found in big heavy-duty trucks. However, they are also used in some pickup trucks. Although the construction of a gasoline and diesel engines is similar, their operation is quite different. A gasoline engine relies on a mixture of fuel and air that is ignited by a spark to produce power. A diesel engine also uses fuel and air, but it doesn't need a spark to cause ignition. A diesel engine is often called a compression ignition engine. This is because its incoming air is tightly compressed, which greatly raises its temperature. The fuel is then injected into the compressed air, and the heat of the compressed air ignites the fuel and combustion takes place. Let's move to discuss the engine parts. We have the cylinder block. The biggest part of the engine is the cylinder block, which is also called an engine block. The cylinder block is a large casting of metal, cast iron or aluminum that is drilled with holes to allow for the passage of lubricants and coolant through the block and provide spaces for movement of mechanical parts. The block contains the cylinders, which are round passageways fitted with the pistons. The block houses or holds the major mechanical parts of the engine. Another important part is the cylinder head. The cylinder head fits on top of the cylinder block to close off and seal the top of the cylinders. The combustion chambers is an area into which the air-fuel mixture is compressed and burned. The cylinder head contains all or most of the combustion chamber. The cylinder head also contains ports, which are passageways through which the air-fuel mixture enters and burned gases exit the cylinder. A cylinder head can be made of a cast iron or aluminum. Also, let's discuss right now the piston. The burning of air and fuel takes place between the cylinder head and the top of the piston. The piston is a can-shaped part closely fitted inside the cylinder. In a 4-stroke cycle engine, the piston moves through 4 different movements or strokes to complete one cycle. These 4 are the intake, compression, power, and exhaust strokes. On the intake stroke, the piston moves downward and charge of air-fuel mixture is introduced into the cylinder. As the piston travels upward, the air-fuel mixture is compressed in preparation for burning. Just before the piston reaches the top of the cylinder, ignition occurs and combustion starts. The pressure of expanding gases forces the piston downward on its power stroke. When it moves upward again, the piston is on exhaust stroke. During the exhaust stroke, the piston pushes the burned gases out of the cylinder. Another part of the engine is the connecting rods and the crankshaft. The reciprocating motion of the pistons must be converted to rotary motion before it can drive the wheels of the vehicles. This conversion is achieved by linking the piston to crankshaft with a connecting rod. As the piston is pushed down on the power stroke, the connecting rod pushes on the crankshaft, causing it to rotate. The end of the crankshaft is connected to the transmission to continue the power flow through the drivetrain and to the wheels. So we have the valve train. A valve train is a series of parts used to open and close the intake and exhaust ports. A valve is a movable part that opens and closes passageway. A camshaft controls the movement of the valves, causing them to open and close at the proper time. Springs are used to help close the valves. Also, we have the manifolds. A manifold is a metal ductwork assembly used to direct the flow of gases to or from the combustion chambers. Two separate manifolds are attached to the cylinder head. The intake manifold delivers a mixture of air and fuel to the intake ports. The exhaust manifold mounts over the exhaust ports and carries exhaust gases away from the cylinders. Hello everyone. In this lecture, we are gonna study the engine systems. So I'm gonna present a brief explanation of the systems that help an engine to run and keep running. We'll start right now with the lubrication system. The moving parts of an engine need constant lubrication. Lubrication limits the amount of wear and reduces the amount of friction in the engine. Friction is heat generated when two objects rub against each other. Motor or engine oil is the fluid used to lubricate the engine. Several quarts of oil are stored in an oil pan bolted to the bottom of the engine block. The oil pan is also called the crankcase or oil sump. When the engine is running, an oil pump draws oil from the pan and forces it through oil galleries. These galleries are small passageways that direct the oil to the moving parts of the engine. Oil from the pan passes through an oil filter before moving through the engine. The filter removes dirt and metal particles from the oil. Premature wear and damage to parts can result from dirt in the oil. Regular replacement of the oil filter and oil is an important step in a preventive maintenance program. Also, we have another system which is the cooling system. The burning of the air-fuel mixture in combustion chambers of the engine produces large amount of heat. This heat must not be allowed to build up and must be reduced, and this heat can easily damage and wrap the middle part of an engine. So to prevent this, engines have a cooling system. The most common way to cool an engine is to circulate a liquid coolant through passages in the engine block and cylinder head. An engine can also be cooled by passing air over and around the engine. Few air-cooled engines are used in automobiles today because it's very difficult to maintain a constant temperature at the cylinders. If the engine is kept at a constant temperature, it will run more efficiently. A typical cooling system relies on a water pump, which circulates the coolant through the system. The pump is typically driven by the engine. The coolant is a mixture of water and antifreeze. The coolant is pushed through passages called water jackets in the cylinder block and head to remove heat from the area around the cylinders, combustion chambers. The heat picked up by the coolant is sent to the radiator. Radiator transfers the coolant's heat to the outside air as the coolant flows through its tubes. To help remove the heat from the coolant, a cooling fan is used to pull cool outside air through the fins of the radiator. Also, to raise the boiling point of the cooling system is pressurized to maintain this pressure. A radiator or a pressure cap is fitted to the radiator. A thermostat is used to block off circulation in the system until a preset temperature is reached. This allows the engines to warm up faster, and the thermostat also keeps the engine temperature at a predetermined level because part of the cooling system are located in various spots under the vehicle's hood. Hoses are used to connect these parts and keep the system sealed. Also, another system that we have is the fuel and air system. The fuel and air system is designed to supply the correct amount of fuel mixed with the correct amount of air to the cylinders of the engine. This system also stores the fuel for later use, delivers the fuel to a device that will control the amount of fuel going to the engine, collects and cleans the outside air, delivers outside air to the individual cylinders, and changes the fuel and air ratios to meet the needs of the engine during different operating conditions. The fuel system is made up of different parts. A fuel tank stores the liquid gasoline. Fuel lines carry the liquid from the tank to the other parts of the system. A pump moves the gasoline from the tank through the lines. A filter removes dirt and other particles from the fuel. A fuel pressure regulator keeps the pressure below a specified level. An air filter cleans the outside air before it's delivered to the cylinders. Fuel injectors mix fuel with the air for delivery to the cylinders or directly to the cylinders. And an intake manifold directs the air to each of the cylinders. Another important system is the emission control system. Engines have been engineered in modern day to emit very low amounts of certain pollutants. The pollutants that have been drastically reduced are hydrocarbons, carbon monoxide, and oxides of nitrogen. The Environmental Protection Agency establishes emission standards that limit the amount of these pollutants a vehicle can emit. So to meet these standards, many changes have been made to the engine itself. There also have been systems developed and added to the engine to reduce the pollutants they emit. So we'll mention some of these systems. We have the positive crankcase ventilation (PCV) system. This system reduces hydrocarbon emissions by drawing fuel and oil vapors from the crankcase and sends them into the intake manifold, where they are delivered to and burned in the cylinders. This system prevents the pressurized vapor from escaping the engine and entering into the atmosphere. Also, we have the evaporative emission control system. This system reduces hydrocarbon emissions by drawing fuel vapors from the fuel system and releases them into the intake air to be burned. This system stops these vapors from leaking into the atmosphere. Also, there is another system which is the exhaust gas recirculation (EGR) system. This system introduces exhaust gases into the intake air to reduce the temperatures reached during combustion. This reduces the chances of forming nitrogen oxide during combustion. Also, we have the catalytic converter located in the exhaust system. It allows for the burning or converting of hydrocarbon or carbon oxide and nitrogen oxide into harmless substances such as water. Also, we have the air injection system. This system reduces hydrocarbon emissions by introducing fresh air into the exhaust system to cause minor combustion of the hydrocarbon in the engine's exhaust. So let's move and discuss the exhaust system. During the exhaust stroke, the engine's piston moves up and pushes the burned air fuel mixture or exhaust out of the combustion chamber into the exhaust manifold. From the manifold, the gases travel through the other part of the exhaust system until they are expelled into the atmosphere. The exhaust system is designed to direct toxic exhaust fumes away from the passenger compartment to quiet the sound of the exhaust pulses and to burn or catalyze pollutants in the exhaust. A typical exhaust system contains the following components: exhaust manifold and gasket, exhaust pipe, seal and connector pipe, intermediate pipes, catalytic converter, muffler and resonator, and tailpipe, heat shields, clamps, gaskets, and hangers. Let's move right now to the electrical and electronic systems. Automobiles have many circuits that carry electrical current from the battery to individual components. The total electrical system includes such major subsystems as the ignition system and the starting system, charging system, and the lighting and other electrical systems. And let's start with the ignition system. After the air-fuel mixture has been delivered to the cylinder and compressed by the piston, it must be ignited. A gasoline engine uses an electrical spark to ignite the mixture. Generating this spark is the role of the ignition system. The ignition coil generates the electricity that creates this spark. The coil transforms the low voltage of the battery into a burst of 30,000 to 100,000 volts. This burst is what ignites the mixture. The mixture must be ignited at the proper time in order to complete combustion to occur, although the exact proper time varies with engine design. Ignition must occur at a point before the piston has completed its compression stroke. On most engines, the motion of the piston and the rotation of the crankshaft are monitored by a crankshaft piston sensor. The sensor electronically tracks the piston of the crankshaft and relays that information to an ignition control module. Based on input from the crankshaft piston sensor, and in some systems the electronic engine control, the computer, the ignition control module then turns the battery current to the coil on and off at just the precise time so that voltage surge arrives at the cylinder at the right time. The voltage surge from the coil must be distributed to the correct cylinder because only one cylinder is fired at a time. In earlier systems, this was the job of the distributor. A distributor is driven by a gear on the camshaft at 1/2 of the crankshaft speed. It transfers the high voltage surge from the coil to spark plug wires in the correct firing order. The spark plug wires then delivers the high voltage to the spark plugs, which are screwed into the cylinder head. The voltage jumps across a space between the two electrodes on the end of each spark plug and causes a spark. This spark ignites the air-fuel mixture. Today's ignition systems do not use a distributor. Instead, these systems have several ignition coils, one for each spark plug or pair for spark plugs. When a coil is activated by electronic control module, high voltage is sent through a spark plug circuit. The electronic control module has total control of the timing and distribution of the spark producing voltage to the various cylinders. And we'll move to the starting and charging systems. The starting system is responsible for getting the engine started. When the ignition key is turned to the start position, a small amount of current flows from the battery to a solenoid or relay. This activates the solenoid or relay and closes another electrical circuit that allows full battery voltage to reach the starter motor. The starter motor then rotates the flywheel mounted on the rear of the crankshaft. As the crankshaft turns, the pistons move through their strokes at the correct time for each cylinder. The ignition system provides the spark to ignite the air-fuel mixture. If good combustion takes place, the engine will now rotate on its own without the need of the starter motor. The ignition key is now allowed to return to the on position. From this point on, the engine will continue to run until the ignition key is turned off. The electrical power of the engine and the rest of the car comes from the car's battery. The battery is especially important for the operation of the starting system. While the starter is rotating the crankshaft, it uses a lot of electricity. This tends to lower the amount of power in the battery. Therefore, a system is needed to recharge the battery so that engine starts can be made in the future. The charging system is designed to recharge and maintain the battery states of a charge. Also, it provides electrical power for the ignition system, air conditioner, heater, lights, radio,
and all electrical accessories when the engine is running. The charging system includes an AC generator, voltage regulator, indicator light, and the necessary wiring, rotated by the engine's crankshaft through a drive belt. The AC generator converts mechanical energy into electrical energy. The AC is converted into direct current (DC) within the alternator. When the output of electrical current from the charging system flows back to the battery is being charged, and when the current flows out of the battery is said to be discharging. And we'll move right now to the electronic engine controls. Nearly all vehicles on the road have an electronic engine control system. This is a system comprised of many electronic and electromechanical parts. The system is designed to continuously monitor the operation of the engine and to make adjustments that will cause the engine to run more efficiently. Electronic engine control systems have dramatically improved fuel mileage, engine performance, and drivability and have greatly reduced exhaust emissions. Electronic control systems have three main types of components: input sensors, a computer, and output devices. The computer analyzes data from the input sensors. Then, based on the inputs and the instruction held in its memory, the computer directs the output devices to make the necessary changes in the operation of some engine systems. So electronic control systems have fewer moving parts than old-style mechanical and vacuum controls. Therefore, the engine and other support systems can maintain their collaboration almost indefinitely. As an added advantage, an electronic control system is very flexible. Because it uses computers, it can be programmed to meet a variety of vehicle engine combinations or collaborations. Critical quantities that determine an engine performance can be changed easily by changing data that is stored in computer's memory. Also, we have the onboard diagnostics. Today's engine control systems are onboard diagnostic second generation systems, or OBD the second. These systems were developed to ensure proper emission control system operation for the vehicle's lifetime by monitoring emission-related components and systems for deterioration and malfunction. This monitoring includes also a check of the tank ventilation system for vapor leaks. The OBD system consists of the engine and the transmission control modules and their sensors and actuators along with the diagnostic software. The computer can detect system problems even before the driver notices a drivability problem, because many problems that affect emissions can be electrical or even chemical in nature. When the OBD system determines that problems exist, a corresponding diagnostic trouble code is stored in the computer's memory. The computer also illuminates a yellow dashboard light indicating a check engine or service engine soon, or displays an engine symbol. This light informs the driver of the need for service, not of the need to stop the vehicle. A blinking or flashing dashboard lamp indicates a rather severe level of engine misfire. When this occurs, the driver should reduce engine speed and load and have the vehicle serviced as soon as possible. After the problem has been fixed, the dashboard lamp will turn off. Also, another system that we have is the heating and air conditioning systems. And let's start with the heating systems. To meet federal safety standards, all vehicles must be equipped with passenger compartment heating and windshield defrosting systems. The main components of an automotive heating system are the heater core, the heater control valve, the blower motor, and the fan, and the heater and defroster ducts. The heating system works with the engine's cooling system and converts the heat from the coolant circulating inside the engine to hot air, which is blown into passenger compartment. A heater hose transfer hot coolant from the engine to the heater control valves and then to the heater core inlet. As the coolant circulates through the core, heat is transferred from coolant to the tubes and fins of the core. Air blown through the core by the blower motor and fan then picks up heat from the surface of the core and transfers it into passenger compartment. After giving up its heat, the coolant is then pumped out through the heater core outlet, where it's turned to the engine's cooling system to be heated again. Transferring heated air from the heater core to the passenger compartment is the job of the heater and defroster ducts. The ducts are typically part of a large plastic shell that connects to the necessary inside and outside vents. Contained inside the duct are also the doors required to direct air to the floor, dash, and windshield. Also, we have the air conditioning systems. An air conditioning system, or AC, is designed to pump heat from one point to another. In an automotive AC system, heat is removed from the passenger compartment and moved to the outside of the vehicle. The substances used to remove heat from the inside of the vehicle is called the refrigerant. To understand how a refrigerant is used to cool the interior of a vehicle, the effects of pressure and temperature on it must be first understood. If the pressure of the refrigerant is high, so its temperature. Likewise, if the pressure is low, so is its temperature. Therefore, changing its pressure can change the refrigerant's temperature. To absorb heat, the temperature and the pressure of the refrigerant are kept low. To get rid of the heat, the temperature and the pressure are high. As the refrigerant absorbs heat, it evaporates or changes from liquid to vapor. As it dissipates heat, it condenses and changes from a vapor to a liquid. These two changes of state occur continuously as the refrigerant circulates through the system. An AC system is a closed pressurized system. It consists of a compressor, condenser, receiver, dryer, or accumulator, expansion valve or orifice tube, and an evaporator. The best way to understand the purpose of the components is to divide the system into two sides, the high side and low side. High side refers to the side of the system that is under high pressure and high temperature. Low side refers to the low pressure and low temperature sides. So one of the components of the system is the compressor. The compressor separates the high and low sides of the system. Its primary purpose is to draw the low pressure and low temperature vapor from the evaporator and compress this vapor into high temperature, high pressure vapor. The secondary purpose of the compressor is to circulate or pump the refrigerant through the system. The compressor is located on the engine and is driven by the engine's crankshaft via drive belt. Compressors are equipped with an electromagnetic clutch as part of the compressor pulley assembly. The clutch is designed to engage the pulley to the compressor shaft when the clutch coil is energized. When the clutch is not engaged, the compressor shaft doesn't rotate and the pulley freewheels. The clutch provides a way for turning the compressor on or off. Also, another part that we have is the condenser. The condenser consists of a cold tubing mounted in a series of thin cooling fins to provide maximum heat transfer in a minimum amount of space. The condenser is normally mounted just in front of the vehicle radiator. It receives the full flow of warm air from the movement of the vehicle or airflow from the radiator fan when the vehicle is standing still. The condenser condenses or liquefies the high pressure, high temperature vapor coming from compressor. To do so, it must give up its heat. Very hot high pressure refrigerant vapor enters the inlet at the top of the condenser, and as the hot vapor passes down through the condenser coils, heat moves from the refrigerant into the cooler air that flows across the coils and fins. This loss of heat causes the refrigerant to change from high pressure hot vapor to high pressure warm liquid. The high pressure warm liquid flows from the bottom of the condenser to the receiver or to the refrigerant metering device if an accumulator is used. So what is the receiver or dryer? The receiver or dryer is a storage tank for the liquid refrigerant from the condenser. The refrigerant flows into the receiver tank, which contains a bag of desiccant. What is a desiccant? It's a moisture-absorbing material. The desiccant absorbs unwanted water and moisture in the refrigerant. Also, another part that we have is the accumulator. Most late model systems have an accumulator rather than the receiver or dryer. The accumulator is connected into the low side of the outlet of the evaporator. The accumulator contains a desiccant and is designed to store excess refrigerant. If liquid refrigerant flows out of the evaporator, it will be collected by and stored in the accumulator. The main purpose of an accumulator is to prevent liquid from entering the compressor. Also, another important part that we have is the thermostatic expansion valve or orifice tube. The refrigerant flow to the evaporator must be controlled to obtain maximum cooling while ensuring complete evaporation of the liquid refrigerant within the evaporator. This is the job of the thermostatic expansion valve or TEV. Some people they abbreviate it as TXV, or a fixed orifice tube. The TEV is mounted at the inlet to the evaporator and separates the high pressure side of the system from low pressure side. The TEV regulates the refrigerant flow to the evaporator by balancing the inlet flow to the outlet temperature. Like the TEV, the orifice tube is the dividing point between the high and low pressure sides of the system. However, its metering or flow rate control doesn't depend on comparing evaporator pressure and temperature. Its fixed orifice, the flow rate, is determined by pressure difference across the orifice and by the additional cooling of the refrigerant in the bottom of the condenser after it has changed from vapor to liquid. Also, we have the evaporator. The evaporator, like the condenser, consists of a refrigerant coil mounted in a series of thin cooling fins. The evaporator is usually located beneath the dashboard or instrument panel. The low pressure, low temperature liquid refrigerant from the TEV or orifice tube enters the evaporator as the spray. The heat at the evaporator causes the refrigerant to boil and change into a vapor. Then transfer of heat from the evaporator to the refrigerant causes the evaporator to get cold. Because hot air always moves toward cold air, the hot air from inside the vehicle moves across the evaporator. As the process of heat loss from the air to the evaporator core surface is taken place, any moisture in the air condenses on the outside of the evaporator core and is drained off as a water. This dehumidification of air adds to passenger comfort. Also, we have the refrigerant lines. There are three major refrigerant lines. Suction lines are located between the outlet side of the evaporator and the inlet side or suction side of the compressor. They carry the low pressure, low temperature vapor to the compressor. The discharge or high pressure line connects the compressor to the condenser. The liquid lines connect the condenser to the receiver or dryer and the receiver or dryer to the inlet side of the expansion valve. Through these lines, the refrigerant travels in its path from a gas state to a liquid state, and then to the inlet side of the expansion valve, where it vaporizes at the evaporator.
Hi, in this lecture we are gonna study the drivetrain. The drivetrain is made up of all components that transfer power from the engine to the driving wheels of the vehicle. The exact components used in a vehicle's drivetrain depends on whether the vehicle is equipped with a rear-wheel drive or a front-wheel drive or four-wheel drive. Today, most cars are front-wheel drive. Some larger luxury and performance cars are rear-wheel drive. Most pickup trucks, minivans, and SUVs are also rear-wheel drive vehicles. Power flow in a rear-wheel drive vehicles passes through the clutch or torque converter, manual or automatic transmission, and the drive line. Then it goes through the rear differential and the rear driving axles and into the rear wheels. Power flow through the drivetrain or front-wheel drive vehicles passes through the clutch or torque converter, then moves through a front differential, the driving axle, and into the front wheels. The four-wheel drive or all-wheel drive vehicles combine features of both rear and front-wheel drive systems so that power can be delivered to all wheels either on a permanent or on-demand basis. Typically, if a truck pickup or SUV has a four-wheel drive, the system is based on a rear-wheel drive and the front drive axle is added. When a car has all-wheel drive or four-wheel drive, the drivetrain is a modified front-wheel drive system. A modification includes a rear drive axle and an assembly that transfers some of the power to the rear axle. We'll start with the first component, which is the clutch. Clutch is used with a manual transmissions and transaxles. It mechanically connects the engine's flywheel to the transmission or transaxle input shaft. This is accomplished by a special friction plate that is splinted to the input shaft of the transmission. When the clutch is engaged, the friction plate contacts the flywheel and transfers power to the input shaft. When stopping, starting, and shifting from one gear to the next, the clutch is disengaged by pushing down on the clutch pedal. This moves the clutch plate away from the flywheel, stopping power flow to the transmission, and the driver can then shift gears without damaging the transmission or transaxle. Releasing the clutch pedal, re-engage the clutch and allows power to flow from the engine to the transmission. And let's move to the manual transmission. A manual or standard transmission is one in which the driver manually selects the gear of choice. Proper gear selection allows for good drivability and requires some driver education. Whenever two or three gears have their teeth meshed together, a gear set is formed. The movement of one gear in the set will cause the others to move. If any of the gears in the set are different size than the others, the gears will move at different speed. The size ratio of the gear set is called the gear ratio of that gear set. A manual transmission houses a number of individual gear sets, which produce different gear ratios. The driver selects the desired operating gear or gear ratio. A typical manual transmission has 4 or 5 forward gear ratios in neutral and reverse. Also, we have the automatic transmission. An automatic transmission doesn't need a clutch pedal and shift through the forward gears. Without the control of the driver, instead of a clutch, It uses a torque converter to transfer power from the engine's flywheel to the transmission input shaft. The torque converter allows for a smooth transfer of power at all engine speeds. Shifting in an automatic transmission is controlled by a hydraulic or electronic control system. In a hydraulic system, a network of valves and other components use hydraulic pressure to control the operation of planetary gear sets. These gear sets provide the 3 or 4 forward speeds, neutral, park, and reverse gears, normally found in an automatic transmissions. Newer electronic shifting systems use electric solenoids to control shifting mechanisms. Electronic shifting is precise and can be varied to suit certain operating conditions. All automatic transmission equipped vehicles with OBD2 have electronic shifting. Also, another part that we have is the drive line. Drive lines are used in rear-wheel drive vehicles and four-wheel drive vehicles. They connect the output shaft of the transmission to the gearing in the rear axle housing. They are also used to connect the output shaft to the front and rear axle drive on a four-wheel drive vehicle. A drive line consists of a hollow drive or a propeller shaft that is connected to the transmission and the drive axle differential by universal joint or U-joints. These U-joints allow the drive shaft to move with a movement of the rear suspension, preventing damage to the shaft. Also, another part that we have is the differential. On a rear-wheel drive vehicle, the drive shaft turns perpendicular to the forward motion of the vehicle. The differential gearing in the rear axle housing is designed to turn the direction of the power so that it can be used to drive the wheels of the vehicle. The power flows into the differential, where it changes direction, then it flows to the rear axles and wheels. The gearing in the differential also multiplies the torque it receives from the drive shaft by providing a final gear reduction. Also, it divides the torque between the left and right driving axles and wheels, so the differential wheel speed is possible. This means one wheel can turn faster than the other when going around turns. Also, we have the driving axles. Driving axles are solid steel shafts that transfer the torque from the differential to the driving wheels. A separate axle shaft is used for each driving wheel in a rear-wheel drive vehicle. The driving axles are part of the differential and are enclosed in an axle housing that protects and supports these parts. Some rear drive axle units are mounted to an independent suspension, and the drive axle assembly is similar to that of a front-wheel drive vehicle. Each drive axle is connected to the side gears and the differential. The inner ends of the axle are splinted to fit into the side gears. As the side gears are turned, the axle to which they are splinted turn at the same speed. The drive wheels are attached to the outer ends of the axle. The outer end of each axle has a flange mounted to it. A flange is a rim for attaching one part to another part. The flange, fitted with studs at the end of an axle, holds the wheel in place. Studs are threaded shafts resembling bolts without heads. One end of the stud is screwed or pressed into the flange. The wheel fits over the studs, and nut, called the lug nut, is tightened over the open end of the stud. This holds the wheel in place. The differential carrier supports the inner end of each axle. A bearing inside the axle housing supports the outer end of the axle shaft. This bearing, called the axle bearings, allows the axle to rotate smoothly inside the axle housing. Also, we have the transaxle. A transaxle is used in a front-wheel drive vehicles. It's made up of a transmission and differential housed in a single unit. The gear set in the transaxle provides the required gear ratios and direct the power flow into the differential. The differential gearing provides the final gear reduction and splits the power flow between the left and right drive axles. The drive axles extend from the sides of the transaxles. The outer ends of the axles are fitted to the hubs of the drive wheels. Constant velocity or CV joints mounted on each end of the drive axles allows for changes in length and angle without affecting the power flow to the wheels. Also, we have the four-wheel drive system. A four-wheel drive system or all-wheel drive vehicles combine the features of a rear-wheel drive transmissions and front-wheel drive transaxles. Additional transfer case gearing splits the power flow between a differential driving the front wheels and a rear differential that drives the rear wheels. This transfer case can be a housing bolted directly to the transmission, or it can be a separate housing mounted somewhere in the drive line. Most rear-wheel drive-based four-wheel drive vehicles have a drive shaft connecting the output of the transmission to the rear axle and another connecting the output of the transfer case to the front drive axle. Typically, all-wheel drive cars have a center differential which splits the torque between the front and rear drive axles. Hello everyone. In this lecture we are gonna study the running gear. The running gear of a vehicle includes those parts that are used to control the vehicle, which includes the wheels and tires and the suspension, steering and the brake systems. And let's start with the suspension system. The suspension system includes such components as the springs, shock absorbers, microphone struts, torsion bars, axles, and connecting linkages. These components are designed to support the body and the frame, the engine and the drive lines. Without these systems, the comfort and ease of driving the vehicle would be reduced. Springs or torsion bars are used to support the axles of the vehicles. The two types of springs commonly used are the coil spring and the leaf spring. Torsion bars are also used and are long spring steel rods. One end of the rod is connected to the frame, whereas the other end is connected to the removable parts of the axles. As the axles move up and down, the rod twists and acts as a spring. Also, we have the shock absorbers, dampen the upward and downward movement of the springs. This is necessary to limit the car's reaction to a bump in the road. Also, we have the steering system. The steering system allows the driver to control the direction of the vehicle. It includes the steering wheel, steering gear, steering shaft, and the steering linkage. Two basic types of steering systems are used today, the rack and pinion and recirculating ball systems. The rack and pinion system is commonly used in passenger cars. The recirculating ball system is normally used only on pickup trucks, SUVs, and full-size luxury cars. Steering gears provide a gear reduction to make changing in the direction of the wheels easier. On most vehicles, the steering gear is also power-assisted to ease the effort of turning the wheels. In a power-assisted system, a pump provides hydraulic fluid under pressure to the steering gear. Pressurized fluid is directed to one side of the other of the steering gear to make it easier to turn the wheels. Some vehicles are equipped with speed-sensitive power steering systems. These change the amount of power assist according to the vehicle speed. Power assist is the greatest when the vehicle is moving slowly and decreases as speed increases. Also, another system we have is the brakes. Obviously, the brake system is used to slow down and stop a vehicle. Brakes located at each wheel use friction to slow and stop a vehicle. The brakes are activated when the driver passes down on the brake pedal. The brake pedal is connected to a plunger in a master cylinder, which is filled with a hydraulic fluid. As the pressure is put on the brake pedal, a force is applied to the hydraulic fluid in the master cylinder. This force is increased by the master cylinder and transferred through brake hoses and lines to the four brake assemblies. Two types of brakes are used: disc brakes and drum brakes. Many vehicles use a combination of the two types: disc brakes at the front wheels and drum brakes at the rear wheels. Others have disc brakes at all wheels. Most vehicles have power-assisted brakes. Many vehicles use a vacuum brake booster to increase pressure applied to the plunger in the master cylinder, while others use hydraulic pressure from the power steering pump to increase the pressure on the brake fluid. Both of these systems lessen the amount of pressure that must be applied to the brake pedal and increase the responsiveness of the brake system. Nearly all late model vehicles have an anti-lock brake system, ABS. The purpose of ABS is to prevent skidding during hard braking to give the driver control of the vehicle during hard stops. The only contact a vehicle has with the road is through its tires and wheels. Tires are filled with air and made of forms of rubber and other materials to give them strength. Wheels are made of metal and are bolted to the axles or spindles. Wheels hold the tires in place. Wheels and tires come in many different sizes. Their sizes must be matched to one another and to the vehicle. Hi, in this lecture we are gonna study the hybrid vehicles. A hybrid electric vehicle, HEV, uses one or more electric motors and an engine to propel the vehicle. Depending on the design of the system, the engine may move the vehicle by itself, assist the electric motor while it's moving the vehicle, or it may drive a generator to charge the vehicle's batteries. The electric motor may power the vehicle by itself or assist the engine while it's propelling the vehicle. Many hybrids rely exclusively on the electric motors during slow speed operation, the engine at higher speeds, and both during some certain driving conditions. Complex electronic controls monitor the operation of the vehicle. Based on the current operating conditions, electronics control the engine, electric motor, and generator. A hybrid's electric motor is powered by high-voltage batteries which are recharged by generator driven by the engine and through regenerative braking. A regenerative braking is the process by which vehicle kinetic energy can be captured while it's decelerating and braking. The electric drive's motor becomes generators driven by the vehicle's wheel. These generators take the kinetic energy or the energy of the moving vehicle and changes it into energy that charges the batteries. The magnetic forces inside the generator cause the drive wheels to slow down. A conventional brake system brings the vehicle to a safe stop. The engines used in hybrids are specially designed for the vehicle and electric assist. Therefore, they can operate more efficiently, resulting in a very good fuel economy and very low emissions. Hybrid electric vehicles, or HEVs, can provide the same performance, if not better, as a comparable vehicle equipped with a larger engine. There are primarily two types of hybrids: the parallel and the series designs. A parallel HEV uses either the electric motor or the gas engine to propel the vehicle, or both. The engine in a true series HEV is used only to drive the generator to keep the batteries charged. The vehicle is powered only by the electric motors. Most current HEVs are considered as having a series parallel configuration because they have the features of both designs. Although most current hybrids are focused on a fuel economy, the same ideas can be used to create high-performance vehicles. Hybrid technology is also influencing off-the road performance by using individual motors at the front and rear drive axles. Additional power can be applied to certain drive wheels when needed.
Hello everyone. In this lecture we are gonna study in depth the automotive engine. As we all know, the engine provides the power to drive the vehicle's wheels. All automobile engines, both gasoline and diesel, are classified as internal combustion engines because the combustion or burning that creates energy takes place inside the engine. The biggest part of the engine is the cylinder block. The cylinder block is a large casting of metal that is drilled with holes to allow for the passage of lubricants and coolant through the block and provide spaces for movement of mechanical parts. The block contains the cylinders, which are round passageways fitted with pistons. The block hoses or holds the major mechanical parts of the engine. The cylinder head fits on top of the cylinder block to close off and seal the top of the cylinder. The combustion chamber is an area into which the air-fuel mixture is compressed and burned. The cylinder head contains all or most of the combustion chamber. So the cylinder head also contains ports through which the air-fuel mixture, innards, and burned gases exit the cylinder and the bore for the spark plug. The valve train is a series of parts used to open and close the intake and exhaust parts. A valve is a movable part that opens and closes the ports. A camshaft controls the movement of the valves, and the springs are used to help close the valves. The up and down motion of the pistons must be converted to rotary motion before it can drive the wheels of the vehicle. This conversion is achieved by linking the piston to crankshaft with a connecting rod. The upper end of the connecting rod moves with the piston. The lower end of the connecting rod is attached to the crankshaft and moves in a circle. The end of the crankshaft is connecting to the flywheel or flexor plate.
So we'll talk right now about engine classifications. As we all know, today's automotive engines can be classified in several ways depending on the following design features. Operational cycles. Most technicians will generally come in contact with only 4-stroke engines. However, a few older cars have used, and some cars in the future will use, the 2-stroke engine. Number of cylinder. Current engine designs include 3, 4, 5, 6, 8, 10, and 12 cylinders engines. Cylinder arrangement. An engine can be flat, opposite, inline, or V-tube. Other more complicated designs have also been used. Also, we have the valve train type. Engine valve train can be either the overhead camshaft OHC type or the camshaft in a block overhead valve or OHV type, and some engines separate camshafts for the intake and exhaust valves. They are based on the OHC design and are called double overhead camshaft or DOHC engines. V-type DOHC engines have 4 camshafts, 2 on each side. Ignition type. There are 2 types of ignition systems, spark and compression. Gasoline engine uses spark ignition system In a spark ignition system, the air-fuel mixture is ignited by an electrical spark. Diesel engine or compression ignition engines have no spark plugs. A diesel engine relies on the heat generated as air compressed to ignite the air-fuel mixture for the power stroke. Also, cooling system, there are both cooled and liquid-cooled engines in use. Nearly all of today's engines have liquid cooling system. Fuel type, several types of fuel currently used in automobile engines include gasoline, natural gas, methanol, diesel, and propane, and the most commonly used is gasoline, although new fuels are being tested. So the four-stroke gasoline engine, in passenger car or truck, the engine provides the rotating power to drive the wheels through the transmission and driving axles. All automotive engines, both gasoline and diesel, are classified as internal combustion because the combustion or burning takes place inside the engine. These systems require an air-fuel mixture that arrives in combustion chamber at the correct time and an engine constructed withstand the temperatures and pressures created by the burning of thousands of fuel droplets. So the combustion chamber is the space between the top of the piston and the cylinder head. It's an enclosed area in which the fuel and air mixture is burned. So the piston fits into a hollow metal tube called a cylinder, and the piston moves up and down in the cylinder. And this reciprocating motion must be converted to a rotary motion before it can drive the wheels of vehicle. This change of motion is accomplished by connecting the piston to a crankshaft with a connecting rod, and the upper end of the connecting rod moves with the piston as it moves up and down in the cylinder. The lower end of the connecting rod is attached to the crankshaft and moves in a circle, and the end of the crankshaft is connected to the flywheel, which transfers the engine's power through the drivetrain to the wheels. In order to have a complete combustion in an engine, the right amount of fuel must be mixed with the right amount of air. The mixture must be compressed in a sealed container, then choked by the right amount of heat, which is the spark, at the right time. So when these conditions exist, all the fuel that enters the cylinder is burned and converted to power, which is used to move the vehicle, and automotive engines have more than one cylinder. Each cylinder should receive the same amount of air, fuel, and heat if the engine is to run efficiently. Although the combustion must occur in a sealed cylinder, the cylinder must also have some means of allowing heat, fuel, and air into it. There must also be a means to allow the burn air-fuel mixture out so the fresh mixture can enter and the engine can continue to run. So in order to accommodate these requirements, engines are fitted with valves. There are at least two valves at the top of each cylinder. The air-fuel mixture enters the combustion chamber through an intake valve and leaves after having been burned through an exit valve. The valves are accurately machined plugs that fit into machined openings. So a valve is said to be seated or closed when it rests in its opening. When the valve is pushed off its seat, it opens. A rotating camshaft driven and timed to the crankshaft opens and closes the intake and exhaust valves. Cams are raised sections of the shaft that have high spot called loops. Cam loops are oval shaped, and the placement of the loop on the shaft determines when the valve will open. The height and shape of the loop determines how far the valve will open and how long it will remain open in relation to piston movement. So the camshaft rotates, the loop rotates and push the valve open by pushing it away from its seat. Once the cam loop rotates out of the way, the valve forced by spring closes, and the camshaft can be located either in the cylinder block or in the cylinder head. So when the action of the valves and the spark plug is properly timed to the movement of the piston, the combustion cycle takes the place in 4-stroke of the piston, and the intake stroke, the compression stroke, and the power stroke, and the exhaust stroke, and the camshaft is driven by the crankshaft through gears or sprockets and cogged belt or timing chain, and the camshaft turns at half of the crankshaft speed and rotates one complete turn during each complete 4-stroke cycle. So we have the 4-stroke cycle. A stroke is the full travel of the piston either up or down in a cylinder's bore, and the reciprocal movement of the piston during the 4-stroke is converted to a rotary motion by the crankshaft. It takes 2 full revolutions of the crankshaft to complete the 4-stroke cycle. 1 full revolution of the crankshaft is equal to 360 degrees of the rotation, and therefore it takes 720 degrees to complete the 4-stroke cycle. During 1 piston stroke, the crankshaft rotates 180 degrees. The flywheel, we have the flywheel. As we know, flywheel, the piston moves by the pressure produced during combustion, but this moves the piston only about half a stroke or 1/4 of a revolution of the crankshaft. This explains why flywheel is needed. The flywheel stores some of the power produced by the engine, and the power is used to keep the pistons in motion during the rest of the 4-stroke cycle. A heavy flywheel is only found on engine equipped with manual transmission. Engines with automatic transmissions have a flex plate and a torque converter. The weight and motion of the fluid inside the torque converter serve as a flywheel. The intake stroke, which is the first stroke of the cycle, is the intake stroke. As the piston moves away from the top dead center, the intake valve opens, the downward movement of the piston increases, and the volume of the cylinder above it, reducing the pressure in the cylinder, and the reduced pressure, commonly referred to as engine vacuum, causes the atmospheric pressure to push a mixture of air and fuel through the open intake valve. So some engines are equipped with a super or turbocharger that pushes more air past the valve. As the piston reaches the bottom of the stroke, the reduction in pressure stops, causing the intake of air-fuel mixture to slow down. It doesn't stop because the weight and the movement of the air-fuel mixture. It continues to enter the cylinder until the intake valve closes, and the intake valve closes after the piston had reached bottom dead center or BDC. This delayed closing of the valve increases the volumetric efficiency of the cylinder by packing as much air and fuel into it as possible. The compression stroke begins as the piston starts to move from BDC. The intake valve closes, trapping the air-fuel mixture in the cylinder, and the upward movement of the piston compresses the air-fuel mixture, this heating it up. At the TDC, the piston and cylinder walls from the combustion chamber and which the fuel will be burned, the volume of the cylinder with the piston at the BDC compared to the volume of the cylinder with the piston at TDC determines the combustion ratio of the engine. And we have the power stroke. The power stroke begins as the compressed fuel mixture is ignited. With the valves is still closed, an electrical spark across the electrodes of a spark plug ignites the air-fuel mixture, and the burning fuel rapidly expands, creating a very high pressure against the top of the piston, and this drives the piston down towards the BDC or bottom dead center, and the downward movement of the piston is transmitted through the connecting rod to crankshaft. We have the exhaust stroke. The exhaust valve opens just before the piston reaches the BDC on the power stroke. So the pressure within the cylinder causes the exhaust gas to rush past the open valve and into the exhaust system. Movement of the piston from BDC pushes mostly of the remaining exhaust gas from the cylinder. As the piston nears TDC, the top dead center, the exhaust valves begins to close as the intake valve starts to open. The exhaust stroke completes the 4-stroke cycle, and the opening of the intake valve begins the cycle again. This cycle occurs in each cylinder and is repeated over and over as long as the engine is running. The firing order, as we know, an engine's firing order states the sequence in which an engine's pistons are on their power stroke, and therefore the order in which the cylinder's spark plugs fire. The firing order also indicates the position of all of the pistons in an engine when a cylinder is firing. For example, consider a 4-cylinder engine with a firing order of 1, 3, 4, 2. The sequence begins with pistons number 1 on the compression stroke. During that time, piston number 3 is moving down on its intake stroke, so the number 4 is moving up on its exhaust stroke, and number 2 is moving down on its power stroke. These events are identified by where it needs to happen in order for number 3 to be ready for fire next, and so on. So the firing order of an engine is determined by its design and manufacturer's preferences. So an engine's firing order can be found on the engine or on the engine's emissions label and in service manual. We'll move right now to study the 2-stroke gasoline engine. In the past, several imported vehicles have used 2-stroke engines. As the name implies, this engine requires only 2-stroke of the piston to complete all 4 operations: intake, compression, power, and exhaust. This is accomplished by follows. First, movement of the piston from the BDC, bottom dead center, to TDC, top dead center, completes both intake and compression. The second, when the piston nears TDC, the compressed air-fuel mixture is ignited, causing an expansion of the gases. During this time, the intake and exhaust ports are closed. The third steps, expanding gases in the cylinder, force the piston down, rotating the crankshaft. And the fourth, with the piston at BDC, the intake and exhaust ports are both open, allowing exhaust gases to leave the cylinder and air-fuel mixture to enter. So although the 2-stroke cycle engine is simple in design and lightweight because it lacks a valve train, it has not been widely used in automobiles. It tends to be less fuel efficient and release more pollutants into the atmosphere than 4-stroke engines. Oil is often in the exhaust stream because these engines require constant oil delivery to the cylinders to keep the piston lubricated, and some of these engines require a certain amount of oil to be mixed with the fuel. Hi, in this lecture we are gonna talk about the engine configurations. Depending on the vehicle, either an inline, V-type, slant, or opposite cylinder design can be used. The most popular designs are inline and V-type engines. We'll start with inline engine. In the inline engine design, the cylinders are all placed in a single row. There is one crankshaft and one cylinder head for all of the cylinders. The block is cast so that all cylinders are located in the upright position. So inline engine designs have certain advantages and disadvantages. They are easy to manufacture and service. However, because the cylinders are positioned vertically, the front of the vehicle must be higher. This affects the aerodynamic design of the car. Also, aerodynamic design refers to the ease with which the car can move through the air. When equipped with an inline engine, the front of the vehicle can't be made as low as it can with other engine design. The second design is the V-type engine. The V-type engine design has two rows of cylinder located 60 to 90 degrees away from each other. A V-type engine uses one crankshaft which is connected to the pistons on both sides of the V. So this type of engine has two cylinder heads, one over each row of cylinders. One advantage of using a V configuration is that the engine is not as high or long as one with an inline configuration. The front of the vehicle can now be made lower, and this design improves the outside aerodynamics of the vehicle. If 8 cylinders are needed for power, a V configuration makes the engine much shorter, lighter, and more compact. Many years ago, some vehicles had an inline 8-cylinder engine. The engine was very long, and its long crankshaft also caused increased torsional vibration in the engine. So a variation of the V-type engine is with W-type engine. These engines are basically two V-type engines joined together at the crankshaft. This design makes the engine more compact, and they are commonly found in late model of Volkswagens. Also, we have the slant cylinder engine. Another way of arranging the cylinders is in a slant configuration. This arrangement is much like an inline engine, except the entire block has been placed in a slant. The slant engine was designed to reduce the distance from the top to the bottom of the engine, and vehicles using a slant engine can be designed more aerodynamically. So we have as well the opposite cylinder engine. In this design, two rows of cylinder are located opposite the crankshaft. These engines have common crankshaft and a cylinder head on each bank of cylinders. So Porsches and Supras use this style of engine, commonly called a boxer engine. So boxer engines have a low center of gravity and tend to run smoothly during all operating conditions. And we'll discuss right now the camshaft and valve location. The valves in all modern engines are placed in the cylinder head above the top of the piston. So the valves in many older engine designs were placed to the side of the pistons. So camshafts are located inside the engine block or above the cylinder head. So the placement of the camshaft further describes an engine. We have the overhead valve or OHV, as the same implies. the intake and exhaust valves in an OHV engine are mounted in the cylinder head and are operated by a camshaft located in the cylinder block. This arrangement requires the use of valve lifters and push rods and rocker arms to transfer camshaft rotation to valve movement. We have the overhead cam OHC. An OHC engine also has intake and exhaust valves located in the cylinder head, but as the name implies, the cam is located in the cylinder head in an OHC engine, so the valves are operated directly by the camshaft through a cam flowers or tappets. So engines with one camshaft above a cylinder are often referred to as single overhead camshaft SOHC engines. And now we'll move to the engine location. So the engine is usually placed in one of three locations. In most vehicles, it's located at the front of the vehicle, in front of the passenger compartment, and the front-mounted engines can be positioned either longitudinally or transversely with respect to the vehicle. So the second engine location is a mid-mount position between the passenger compartment and rear suspension. Mid-mount engines are normally transversely mounted. The third and the last common engine location is the rear of the vehicle. The engines are typically opposed-type engines. Each of these engine locations offers advantages and disadvantages. And now we'll move to the front engine longitudinal. In this type of vehicle, the engine, transmission, front suspension, and the steering equipment are installed in the front of the body, and the differential and rear suspension are installed in the rear of the body. Most front engine longitudinal vehicles are rear-wheel drive. Some front-wheel drive cars with a transaxle have this configuration, and most four-wheel drive vehicles are equipped with a transfer case and have the engine mounted longitudinally in the front of the vehicle. Total vehicle weight can be evenly distributed between the front and rear wheels with this configuration. This lightens the steering force and equalizes the braking load with this design. It's possible to independently remove and install the engine, propeller shaft, differential, and the suspension. And we have the front engine transverse. Front engines that are mounted transversely sit sideways in the engine compartment. They are used with a transaxle that combine transmission and differential gearing into a single compact housing. So fastened directly to the engine, transversely mounted engines reduce the size of the engine compartment and overall vehicle weight. Transversely mounted front engines allows for downsized, lighter vehicle with increased interior space. However, most of the vehicle weight is toward the front of the vehicle. This provides for increased traction by the drive wheels, and the weight also places a greater load on the front suspension and the brakes. We have the mid-engine transfers. In this design, the engine and the drivetrain are positioned between the passenger compartment and rear axle. Mid-engine location is used in smaller rear-wheel drive high-performance sport cars for several reasons. The central location of heavy compartment results in a center of gravity very near the center of the vehicle, which vastly improves steering and handling. Since the engine is not under the hood can be sloped downward, improving aerodynamics and increasing the driver field of vision. So, however, engine access and cooling efficiency are reduced. A barrier was also needed to reduce the transfer of noise, heat, and vibration to passenger compartment. Hello everyone. In this lecture we are gonna study engine measurement and performance. We have bore and stroke. The bore of a cylinder is simply its diameter measured in inches or millimeters, and the stroke is the length of the piston travel between the TDC or top dead center and BDC bottom dead center between them, and bore and stroke determine the displacement of the cylinders. When the bore and stroke are of equal size, the engine is called a square engine. Engines that have a larger bore than a stroke are called over square, and engines with a larger stroke than bore are referred to as being under square. Over square engines offer the opportunity to fit a larger valves in the combustion chamber and use longer connecting rods, which means over square engines are capable of running at higher engine speeds, but because of the size of the bore, the engines tend to be physically larger than the under square engines. Under square engines have short connecting rods that aid in the production of more power at lower engine speeds. A square engine is a compromise between the two designs, and the crank throw is the distance from the crankshaft's main bearing center line to the connecting rod journal center line. So the stroke of any engine is twice the crank throw. We have the displacement. A cylinder displacement is the volume of the cylinder when the piston is at BDC. And engine displacement is the sum of the displacements of each of the engine cylinders. So typically, an engine with a larger displacement produces more torque than a smaller displacement engine. However, many other factors influence an engine's power output, and engine displacement can be changed by changing the size of the bore and or stroke of an engine. We have as well the compression ratio. An engine-stated compression ratio is a compression of a cylinder's volume when the piston is at BDC to the cylinder's volume when the piston is at TDC. The compression ratio is a statement of how the air-fuel mixture is compressed during the compression stroke. So it's important to keep in mind that this ratio can change through wear and carbon and dirt built up in the cylinders. Also, the higher the compression ratio, the more power an engine theoretically can produce. Also, as the compression ratio increases, the heat produced by the compression stroke also increases. So gasoline with a low octane rating burns fast and may explode rather than burn when introduced to a high compression ratio, which can cause pre-ignition. The higher gasoline octane rating, the less likely it's to explode. As the compression ratio increases, the octane rating of the gasoline should also be increased to prevent abnormal combustion. Also, we'll discuss right now the engine efficiency. So we have a different factor to measure the engine efficiency. Let's start with the volumetric efficiency. Volumetric efficiency describes the engine's ability to have its cylinders filled with air-fuel mixture, and if the engine cylinders are able to be filled with air-fuel mixture during its intake stroke, the engine has a volumetric efficiency of 100%. Typically, engines have a volumetric efficiency of 80 to 100 if they are not equipped with a turbo or supercharger. Basically, an engine becomes more efficient as its volumetric efficiency is increased. Also, we have the mechanical efficiency. Mechanical efficiency is a measure of how much power is available once it leaves the engine compared to the amount of power that was exerted on the pistons during the power stroke. Power losses occur because of the friction generated by the moving parts. Minimizing friction increases mechanical efficiency. And we have the thermal efficiency. Thermal efficiency is a measure of how much of the heat formed during the combustion process is available as power from the engine. And we'll discuss right now what's the difference between torque and horsepower. Torque is a twisting or turning force. Horsepower is the rate at which torque is produced. An engine produces different amount of torque based on the rotational speed of the crankshaft and other factors. And also we have the mathematical representation in this graph shown here. This graph shows that torque begins to decrease when the engine's speed reaches about 1,700 rounds per minute. A brake horsepower increases steadily until about 3,500 rounds per minute, then it drops. The third line on the graph indicates the horsepower needed to overcome the friction or resistance created by the internal parts of the engine rubbing against each other. A brake horsepower is a term used to express the amount of horsepower measured on a dynamometer, and this measurement represents the amount of horsepower an engine provides when it's held at a specific speed at full throttle. So horsepower is also expressed as SEE, gross horsepower, which is the maximum amount of power an engine produces at a specified speed with some of its accessories disconnected or removed. So SAE, net horsepower, represents the power produced by an engine at a specified speed when all of its accessories are operating. Hi, in this lecture we are gonna study the diesel engines. So, the diesel engine is now the dominant power plant in heavy-duty trucks, construction equipment, farm equipment, buses, and marine applications. The operation of a diesel engine is comparable to a gasoline engine. They also have a number of components in common, such as the crankshaft, pistons, valves, camshaft, and water and oil pumps. They both are available as 2 or 4-stroke combustion cycle engines. But however, diesel engines have compression ignition systems. Rather than relying on a spark for ignition, a diesel engine uses the heat produced by compressing air in the combustion chamber to ignite the fuel. So the compression ratio of diesel engine is typically 3 times that of a gasoline engine. As intake air is compressed, its temperature rises to 1,650 Fahrenheit, around 900 Celsius, between 700 to 900 Celsius degree. Just before the air is fully compressed, a fuel injector sprays a small amount of diesel fuel into the cylinder. The high temperature of the compressed air instantly ignites the fuel, so the combustion causes increased heat in the cylinder, and the resulting high pressure moves the piston down on its power stroke. Diesel engines are heavier than gasoline engines. Also, a diesel engine must be made stronger to contain the extremely high compression and combustion pressure. A diesel engine also produces less horsepower than same-sized gasoline engine. Therefore, to provide the required power, the displacement of the engine is increased. This results in a physically larger engine, and diesel have high torque output at very low engine speeds but do not run well at high engine speeds. On many diesel engines, turbochargers and intercooler are used to increase their power output. Diesel combustion chambers are different from gasoline combustion chambers because diesel fuel burns differently. Three types of combustion chambers are used in diesel engines: open combustion chamber, pre-combustion chamber, and turbulent combustion chamber. The open combustion chamber is located directly inside the piston. Diesel fuel is injected directly into the center of the chamber, and the shape of the chamber and the quench area produce turbulence. And the pre-combustion chamber is a smaller second chamber connection to the main combustion chamber. On the power stroke, fuel is injected into the small chamber. Combustion is started there and then spreads to the main chamber. This design allows for lower fuel injection pressures and simpler injection systems. The turbulent combustion chamber creates an increase in air velocity or turbulence in the combustion chamber. The fuel is injected into the turbulent air and burns more completely. Fuel injection is used on all diesel engines. Older diesel engines had distributor-type injection pump driven and regulated by the engine. Also, the pump supplies fuel to injector that sprayed the fuel into the engine combustion chamber. Newer diesel engines are equipped with common rail system. Common rail system are direct injection or DI systems. The injector nozzles are placed inside the combustion chamber, and the piston's top has a depression where initial combustion takes place. The injector must be able to withstand the temperature and the pressure inside the cylinder and must be able to deliver a fine spray or fuel into these conditions. Diesel engines are also available in two-stroke cycle models. Most diesels generally use the four-stroke cycle, while some larger diesels operate with a two-stroke cycle. The advantages of diesel engine when compared to a gasoline engines: diesel engines offer many advantages. They are more efficient and use less fuel than gasoline engine of the same size. Diesel engines are very durable. This is due to stronger construction and the fact that diesel fuel is better lubricant than gasoline. This means that the fuel is less likely to remove the desired film of oil on the cylinder walls and piston rings of the engine. Also, diesel engines better suited for moving heavy loads at low speeds. The disadvantages of diesel engine are low power output, difficult cold weather starting, noise, and exhaust emission. So many diesel engines are fit with a turbocharger to increase their power. Combining turbochargers with the common rail injection system have resulted in more horsepower. In cold weather, diesel engines can be difficult to start because the cold air can't become hot enough to cause combustion. In spite of the high compression ratios, this problem is compounded by the fact that the cold middle of the cylinder block and head absorbs the heat generated during the combustion stroke. Some diesel engines use glow plugs to help ignite fuel during cold starting. These small electrical heaters are placed inside the cylinder and are used only to warm the combustion chamber when the engine is cold. Other diesels have a resistive grid heater in the intake manifold to warm the air until the engine reaches operating temperature. And one of the disadvantages of diesel engine is sound. This noise, knock or clatter, is caused by the sudden ignition of the fuel as it's injected into the combustion chamber. Through the use of electronically controlled common rail injector systems, manufacturers have been able to minimize the noise.
Hello everyone. In this lecture we are gonna study the cylinder block. The cylinder block houses the areas where combustion takes place. It's normally a one-piece casting that is machined so that all parts contained in it fit properly. Blocks may be cast from different materials such as iron, aluminum, and magnesium. A few engine blocks have an exterior made of magnesium and the interior of a cast iron insert. Some late model blocks are made of two pieces, an upper unit that contains the cylinder and a lower one that surrounds the crankshaft. Other blocks have main cab griddle integrated in the housing to provide added strength. Cast iron blocks are very strong but heavy. Many engines have an aluminum block to reduce the vehicle's overall weight. Certain materials are added to aluminum to make it stronger and less likely to wrap from the heat of combustion. And the cylinder walls of aluminum blocks may be treated with a special coating or may have a sleeve or liner to serve as cylinder walls. Also, we'll move to the cylinder liners. Most aluminum blocks have cylinder liners. The liners are normally made of a cast iron alloy. On some engines, the liners can be replaced and or machined if they are damaged. Most are very thin and can't be served, and the block must be replaced if the walls are damaged. Liners are pressed into the block or placed in a mold before the block is cast. The liners have ribs on their outside diameter, and these ribs hold the liner in place and increase its ability to dissipate heat to the block. There are two types of sleeves, wet and dry. The dry sleeves is supported from the top to bottom by the block. The wet sleeve is supported only at the top and bottom. Coolant touches the center part of a wet sleeve. As well, we have the lubrication and cooling. A cylinder block contains a series of oil passages that allow engine oil to be pumped through the block and the crankshaft and onto the cylinder head. Water jackets are also cast in the block around the cylinder bores, and coolant circulates through these jackets to transfer heat away. Some engine blocks are cast with a plastic spacer for the water jackets, so the spacer provides a uniform distribution of heat throughout the cylinder by directing the flow of coolant toward the normally hotter areas. For example, a spacer is used to direct coolant away from the center of the cylinder and bore to the top and bottom of the bore. So the top and bottom of the bore are normally the hotter areas. So suppressing the coolant flow to the center may result in the center having the same temperature as the top and bottom.
And we'll study right now the camshafts. A camshaft has a cam for each exhaust and intake valve. Each cam has a loop that controls the opening of the valves. The height of the loop is proportional to the amount of the valve will open. The camshaft in older engines had an eccentric to operate the fuel pump and a gear to drive the distributor and oil pump. Some diesel engines have cam loops for fuel injectors, fuel injection pumps, and air starting valves. The camshaft fits in a bore above the crankshaft. The bore is either in the center of the block or slightly off to one side. Unless the engine has overhead camshafts, many camshafts are cast iron or steel. Others are forged steel units. to reduce weight and added strength. The camshaft in many late model engines is a steel tube with a lobe welded to it. In OHV engines or overhead cams, the camshaft loops work with lifters, push rods, and rocker arms to open the valves. As the cam loop rotates, it pushes up on the lifter, which moves the push rod and one end of the rocker arm up. Since a rocker arm is a lever, as that end goes up, the other moves down. This action pushes down on the valve to open it. As the cam continues to rotate, the valve spring closes the valve while maintaining contact between the valve and the rocker arm, thereby keeping the push and the lifter in contact with the rotating cam. OHC engines may have separate camshafts for the intake and exhaust valves. As these camshafts rotate, the lobe directly open the valves or open them indirectly with cam followers. Rocker arms or bucket type tappets, the closing of the valves is still the responsibility of the valve springs. Service to the camshaft in OHC engine is usually a part of the procedure for reconditioning the engine's cylinder head. A camshaft is driven by a crankshaft at half its speed. So this accomplished is through the use of the camshaft drive gear or drive sprocket that is twice as large as the crankshaft sprockets. So during one full rotation of the camshaft, the intake and exhaust valves open and close once. To synchronize the opening and the closing of the valves with the piston and movement of the pistons, the camshaft is timed to the crankshaft. And the actual design of the cams and loops varies with the type of lifter and follower used in the engine. There are 4 distinct types of lifters: solid non-roller, hydraulic non-roller, solid roller, and a hydraulic roller. Camshafts design of a solid and hydraulic non-roller cams are often called flat tappet cams, and the camshaft must be matched with the type of lifter for which it was designed. And we have the camshaft terminology. Many different terms are used to define the specifications of the camshaft. The actual shape of the cam loop is called the cam profile. The profile determines the duration and lift provided by the camshaft. Valves overlap is controlled by the placement of the loops on the camshaft. Camshaft duration is how long the cam holds the valves open. It's expressed in crankshaft degrees. The width of the loop determines the cam's duration, and lift is the distance the loop moves and the lifter or followers to open the valve. And maximum lift is determined by the height of the loop, and the valve is fully open only when the lifter is at the top of the loop. Camshaft lift doesn't always express how far the valve is open. Rocker arms increase the actual amount of valve opening. Both valves are open slightly at the end of the exhaust stroke and the beginning of the intake stroke. This is called the valve overlap. And overlap is critical to exhaust gas scavenging. A camshaft with a long overlap helps empty the cylinders at high engine speeds for improved efficiency. However, since both valves are open for a longer period, low RPM cylinder pressure tends to drop because the amount of overlap has an effect on cylinder pressure. It affects overall engine efficiency and exhaust emissions, and valve overlap also helps to get the intake mixture moving into the cylinder. As the exhaust gases move out of the cylinder, a low pressure is present in the cylinder. This low pressure causes atmospheric pressure, to push the intake charge into the cylinder. Less overlap provides for more pressure in the cylinder at low speeds, resulting in more torque at lower speeds. Also, we have the loop terminology, and here some terms are used to describe the camshaft's profile. We have the base circle. The base circle is the cam without its loop. Also, we have the nose. The nose is the highest portion of the cam loop measured from the base circle, and this point provides for the maximum amount of lift. We have the ramp, flank, and the ramps are the side of a cam loop that lie between the nose and the base circle. We have clearance ramps. Clearance ramps are at the very beginning or end of the opening and the closing ramps. Also, we have loop separation. Loop separation is the angle formed by the center line of the intake and exhaust loops. And we'll move right now to the timing mechanisms. The camshaft and the crankshaft must always remain in the same relative position to each other. They must also be angled to each other, so the alignment is initially set by matching marks on the gears for both shafts. These are called timing marks, and the following are the basic configuration for driving the camshaft. We have the belt drive, which is sprockets on the crankshaft and the camshaft are linked by a continuous neoprene belt. The belt has square-shaped internal teeth that mesh with teeth on the sprockets, and the timing belt is reinforced with a nylon or fiberglass to give it strength and prevent stretching. This drive configuration is limited to OHC engines. Most technicians replace the belt anytime it has been removed. Also, we have a chain drive. Sprockets on the camshaft and the crankshaft are linked by a continuous chain. The sprocket on the crankshaft is a steel. The sprocket on the camshaft is a steel on a heavy-duty applications. When a quiet operation is gold, an aluminum sprocket with a nylon teeth is used. And nearly all OHV engines use a chain drive system. Chain drives are also used on many OHC engines, especially DOHCs. We have as well the gear drive. A gear on a crankshaft meshes directly with a gear on a camshaft, and the crankshaft gear is usually iron or steel. Also, we have the tensioners. There is a tensioners on a long chain and belt drive, and the tensioners may be spring-loaded and or hydraulically operated. Its purpose is to keep the belt or chain under the correct tension as it wears and stretches. All belts and chains have a drive or tension side and a slack side. The tension side is the side that is always being pulled, and the tensor side is positioned on the slack side and presses on the belt or chain. Also, there is a variable valve timing, or VVT. The variable valve timing, or VVT system, electronically adjusts valve overlap by changing exhaust valve opening times in response to engine speed and load. The system provides an increase in horsepower and torque. It also reduces fuel consumption and exhaust emission. Also, we have the valve lifters. Valve lifters, sometimes called cam followers or tappets, follow the counter or shape of the cam loop. Lifters are either mechanical, solid, or hydraulic. Solid valve lifter provides a rigid connection between the camshaft and the valves. Hydraulic valve lifters provide the same connection but use oil to absorb the shock that results from the movement of the valve train. and hydraulic lifters are designed to automatically compensate for the effects of engine temperature. Changes in temperature cause valve train components to expand and contract. Hydraulic lifters automatically maintain a direct connection between valve train parts. Solid lifters do not have this built-in feature and requires a clearance between the parts of the valve train, and this clearance allows for components expansion as the engine gets hot. Periodic adjustment of this clearance must be made, and excessive clearance might cause a clicking noise, and this clicking noise is also an indication of hammering of valve train parts against one another, which results in reduced camshaft and lifter life. So, non-roller lifters rotate in their bore. The contact area between the cam loop and lifter is one of the highest stressed area in an engine. So lifter rotation places this stress at different areas at the bottom of the lifter and prevent excessive wear. So cam loops are ground with a slight taper, approximately 0.254 millimeter, and the diameter of the front of the loop's base circle is different from the diameter at the rear of the loop. So the speed at which the lifter rotates in its bore depends on the amount of taper. So the interface of the lifter and loop taper also prevents the camshaft from moving to the front or rear while the engine is running. We have as well the roller lifters. In an effort to reduce the friction of the lifter rubbing against the cam loops and the resulting power loss, manufacturers often use roller type lifters, which is roller lifters, and have a roller on the camshaft end on the lifter. Also, the roller acts as a wheel and allows the lifter to follow the corner of the cam loop with a little friction. The lifter rolls along the surface of the loop rather than rub against it, so roller lifters may be solid or hydraulic. The hydraulic part of roller lifter works in the same way as the flight hydraulic tappet. The rollers also allow the lifter to follow aggressive cam loop designs that provide more lift at a given duration than a flat tappet. We'll move right now to the operation of hydraulic valve lifters. A hydraulic lifter has a plunger, oil metering valve, pushrod seat, check valve spring, and a plunger return spring housed in a hardened iron body. When the lifter is resting on a cam's basic circle, the valve is closed and the lifter maintains zero clearance in the valve train. Oil is fed to the lifter through fed holes in its bore. Oil pressure forces the lifter check valve closed to keep the oil inside the lifter, and this forms a rigid connection between the lifter and pushrod. When there is some clearance in the valve train, a spring between the plunger and lifter body pushes the plunger up to eliminate the clearance. As the cam loop turns and opens the valve, the lifter's oil feed hole moves away from the oil feed in the lifter bore. So new oil can't enter the lifter. The effort to open the valve pushes the lifter's plunger down slightly, and this allows a small amount of oil to leak out. This is called leak down. So when the lifter returns to the base of the cam, oil can again fill the lifter. So we have as well the camshaft bearings. The camshaft is supported by several bearings or bushings. OHV camshaft bearings are one-piece plain bearings pressed into the camshaft. Before the bearings are either aluminum or steel with a lining of babbitt. Babbitt is a soft, slippery material made of mostly lead and tin. Alloys of aluminum are commonly found in late model engines. Aluminum bearings have a longer service life because they are harder than pivot, but they are more susceptible to damage from dirt and poor lubrication. So OHC camshaft may be supported by split plane bearings. These split bearings are similar to the main and connecting rod bearings. Camshaft bearings are normally replaced during engine rebuilding, and the old bearing should be inspected for signs of unusual wear that may indicate an oiling or bore alignment problem. Also, we have a balance shaft, has a counterweight designed to mirror the throws of the crankshaft. These weights are positioned to the opposite side of the weight of the crankshaft and are rotated in the opposite direction as the crankshaft. Balance shafts are located in the engine block on one side of the crankshaft, in the camshaft bore, or in separate assembly bolted to the engine block.
Thank you everyone for joining. We're going to end this stream here. We will continue this course if you so wish to watch the rest of it. I'm going to break it down into 4 segments because there are a lot of sections in this. So feel free to join again tomorrow, roughly around the same time, and we'll continue on. And we'll slowly plug away through it over the next couple days. I hope you guys are enjoying this. I could have done this myself and sat here and read all this crap and blah, blah, blah. But you know what? I'm too old for that stuff. So this seems to be the easiest way to get you guys introduced to automotives and automotive mechanicry. So I hope you enjoyed it. And thank you everyone for joining. And hopefully I see you tomorrow for the next part.